All right, well, with some statistics under our belts, we're now prepared to kind of discuss what the best fit line is using linear regression. And before we even talk about the best fit line, we need to discuss or rather define what a residual is. A residual is nothing more than the vertical distance between a data point and that best fit line. Essentially, if I have some data right here, there's 1, 2, 3, 4, 5 data points, and I have some sort of line in between them, the best fit line is going to result in a residual of the distance between these points and the model right here, such that a best fit line in a superlative sense is going to be one that hopefully minimizes the sum of residuals in some sort of way. Well, let's talk about some different ways that we can minimize summations of these residuals. The first one is straight up just minimizing the summation of those residuals. So if we have 2 points right here, and I take a look at the residual right here, which is 0, and the residual right here, which is 0, again, the distance between the data point and the line itself, I'm left with 0 as my sum of the residuals. But another line, let's say another candidate line right here, okay, has two other residuals. One is right here, and one is right here. One of these residuals is going to be negative, the other one is going to be positive, and they're also going to make 0, which means then that the sum of residuals is not a good way of trying to find the best fit line, because there's a whole bunch of different lines that are going to result in the same value. In fact, any line that crosses through this midpoint right here is going to satisfy the sum of residuals is equal to 0, at least with 2 data points. So that's no good. Well, what about the sum of absolute values of residuals? Well, this is also not going to yield a unique best fit line. So for example, let's take a look at this candidate line right here in dashed red. And of course, I have a 0 residual here and a 0 residual here, but I have this vertical distance right here and this vertical distance right here. Sure, that's going to be some sort of value. But if I take a look at another candidate line right here, I'm going to be left with the exact same sum of absolute values of residuals, this distance and this distance. And in fact, any line that passes through these sets of 4 points are going to have residuals, maybe 2 of them, 4 of them, some sort of non-zero values that will result in a whole bunch of non-unique best fit lines. Since best is superlative, we need to find one and only one best fit line that hopefully does a good job, and therefore sum of absolute values of residuals does also not work out very well. Same thing with the maximum error of any one individual point. So for example, the residual for this point, and for this point, and for this point, and this point, and this one are all equal to each other. But you would probably recognize that the best fit line is probably a little bit closer to where a majority of the data points are. Thus, the maximization, or rather minimization of the maximum error of any one individual point gives too much influence to any single outlier points. Therefore, what we found is that using least squares is the optimal way of trying to find the best fit line, a line, one and only one, that can overcome all of these shortcomings from the previous slide, and it's called minimizing the sum of the squares of the residuals. What does that really mean? Well, if you recall, we have right here a residual. The residual is nothing more than the vertical distance between the data, or the points, and the line, the model. If that model, okay, is nothing more than a straight line, a0 plus a1 xi, well, then we know, okay, that the residual will be the data subtracted from the model. If it helps, you can see that y, the line, is going to be b plus mx. Effectively, a1 is the slope, and a0 is the intercept. Well, if this is our model, we're going to try to use a straight best fit line. We subtract these two together, and then we're going to square them, and then we're going to sum up all those things, and that is going to be our equation that will give us only one best fit line. What's important to note is that if we want to define a line, we need two things. We need the intercept, and we need the slope. And we get those two from a0 and a1, which effectively tells us that in this equation right here, we need to solve for these two unknowns. If we have two unknowns and only one equation, we got to do something to find that second equation. We find that second equation by taking partial derivatives with respect to those two unknowns, a0 and a1, and then we set them equal to 0. Again, this is from early days in your calculus where we want to find that minimum point. And so we set something to equal to 0. And then if we can find the solution to that value, well, that will be the value that minimizes that particular function. As a result, if we take the partial derivative of SR with respect to A0, we get this right here. And if we take it with respect to A1, we get this equation right here. And now we're left with two equations with two unknowns that can help us solve for A0 and A1. Well, with those two equations and two unknowns, we can use substitution or anything else, and we're left with then two equations that can be used to solve for A1 and A0. The derivation is not too complicated, but if you want to take your time going from slide 9, the previous slide, to this slide, it takes a little bit of time, but it's not so bad. Effectively, it's the summation of a whole bunch of different things over another ratio, and n is the number of data points that you have inside your data set. Note then that A1 is solved first, and then A1 is used in this formula right here, using substitution to get A0. And again, once you have A1 and A0, you have everything you need to get that model. And that model is a straight line, A0 plus A1x of your data. Well, anytime we have a numerical method, we want to kind of analyze the error, how good it is, or how bad it is. And so we can use that same equation, okay, the sum of squares of the residuals, to figure out if this is a good model or not. Effectively, it helps us determine how well our line describes the data. Now to do so, we're going to compare the error to our fit to the total error of a horizontal line through the mean of the data. So ST, we should think of total error, and SR, we should think of regression error. Essentially, if we take a look at the model, in this particular case, we have a very, very simple model. It's nothing more than the mean of all the data. So essentially, if we have a whole bunch of data, so here's a little bit of line, I'll draw some points right here. There's one model that cuts right through all this data, and it is the mean of all this data. And this right here then could be considered, well, the intercept with a slope of 0. Effectively, this model is the 0th order model, y equals A0. Whereas this one up here is y equals A0 plus A1x. It's got a little bit of a slope. And we're going to try to compare the difference between these two models. Well, we use what's called the correlation coefficient, or R squared value, or it's also called the coefficient of determination, because it shows the error between ST, which is on this side, and SR, which is on this side. So the total error, of course, when we have this line right here, which is nothing more than the average line horizontally of all these data points, and so we have these residuals, and of course we can sum those up, and we get ST in that formulation in the previous slide, or we can get the residuals right here. We can square them, sum them up, and get SR, and then of course we take the difference, and then over the ratio of the total error from this side gives us an R squared value. Well, why do we do this? Well, we want to know how big an improvement our line is over this average value. If there's no improvement, then why are we increasing the complexity of a line that's angled versus just a horizontal line? So for example, if we have a perfect fit, which means then that all of our data points fall directly on the line, okay, all the residuals are equal to 0, which means then the square of those residuals is equal to 0, and therefore the sum of all those squared residuals is equal to 0, which means that this term right here goes to 0, and we're left then with ST over ST, which is equal to 1, right here. On the other hand, for r is equal to 0, we know then that this numerator part is equal to 0, which then tells us that ST is equal to SR, down right here. That's going to tell us then that our new fit represents no improvement over the mean. And so an R value can be anywhere between 0 and 1. An R squared value of 1 means perfect fit. An R squared value of 0, which also means that an R value is equal to 0, means no improvement. You should just stick with your simple mean model to represent the data. In a computer, we usually use this formulation, which is nothing more than kind of a derivation of the ST and SR in this process right here. All right, well, if we're thinking that a first order is pretty good, could we do better with even a second order polynomial? Very similar to other numerical methods in this class. If one segment is good and two segments is even better, for example, like in numerical integration, can we get by with a model that's a little bit more complicated? In this particular case, we're going to have a model that is a second order polynomial. You can see it right there. A quadratic equation. A quadratic equation has three unknowns: a0, a1, and a2. We do the same sort of thing by putting it inside our equation for the sum of squares of the residuals right here. And then, of course, we want to try to minimize this sum of squares of the error. And therefore, we need to try to find what values of a0, or a0, a1, and a2 will minimize this error. Well, same sort of thing. We're going to do the partial derivatives with respect to a0, the partial derivatives with respect to a1, and the partial derivative with respect to a2. And we're left with these three equations right here. Applying the chain rule, of course, we have xi here and xi2 from this term and this term respectively. Since we now have three equations and three unknowns, we can now solve for those coefficients, a0, a1, and a2. If we do some reorganization from the previous slide, we're left with these three equations. They've been put in a format so that we can kind of see how, yes, there is in fact an a0 term in each one, an a1 term, an a2 term in each one, and we've brought all the other stuff to the right-hand side. We take this and convert it into a matrix vector form, and we're left with a square matrix. I'll call this matrix A. A unknown vector. Okay, I'll just call this X for the unknowns, namely a0, a1, and a2. And then the B side vector. Now that we've got it in matrix vector form, we can use different methods to solve for our unknowns, a0, a1, and a2. Of course, in the first example that we showed you in these slides, we only had a0 and a1, and so we could do it by basic substitution. But in this case, we have a whole bunch of other techniques that we can use: Gaussian elimination, LE decomposition, simple matrix inversion. So you can implement your favorite linear solver and figure out what the solution is, and ultimately you can figure out what a0, a1, a2, and am are, if in fact you have more data, or if you want to use it for any polynomial of order m. What's important, of course, is that m must be less than or equal to n minus 1. Essentially, if n is equal to 5 data points, m must be 4 or less than that. Which means then that if I have 5 data points, m can be a fourth order polynomial, a third order polynomial, a second order polynomial, or a first order polynomial. That's that best fit line that most people kind of think about in a first order polynomial sense. In fact, you can even have a zeroth order polynomial, but that's just that mean horizontal line that we talked about that's used for the total error.